Okay, everybody, we found our way to page 17 in the manual, and I'm just going to talk about a few of these parameters as they relate to the lectures and really what you need to understand about drives. First of all, we have our acceleration ramp time and deceleration ramp time. We already identified that they were factory set to 3 seconds each, but right here you can see that we have an adjustment range of 0.1 seconds to 999.9 seconds. So you could essentially make that motor take a really long time to start, or you could set it to a really short time to start. Now, there's a disadvantage to this is that ramp time is not load specific. So if we have a very high inertia load, that would be something that's really, really heavy. It takes a long time to get up and get rolling, but once it does, it wants to keep rolling. Then if you set this acceleration ramp time to 1 second, all that means is the voltage and the frequency are going to increase in 1 second to the maximum rate that you've set. That doesn't mean that the motor will have accelerated in that amount of time. Same with stopping. So deceleration ramp time is a type of stopping method. You can tell the motor to ramp down in, let's say, 5 seconds. But again, if it's a really high inertia load, well, it just won't be stopped in 5 seconds. And then after that deceleration ramp time is done, then the motor will just coast to a stop. So that's not necessarily the safest way to bring a motor to a stop. Next we have low speed and high speed. So this is what you want the low speed and the high speed to be in hertz going out to the motor. So typically it would be 0 to 60 hertz here in North America if we wanted to run a motor up to its rated speed. One of the advantages of a drive is there are certain applications where we can run at a reduced speed, and that actually will correspond to a reduced cost. That only happens with fluid type loads, so gases or liquids. So fans and pumps would be the application for that. Motor thermal protection. This is where we enter the nominal current on the motor nameplate. On to page 19. And on this page here, I just want to talk a little bit about skip frequency. So this is another parameter that we have. And as I'm sure you're all aware, most things have a natural frequency where something occurs called resonance. Now, I'm not talking in the electrical world of things, I'm talking physically. There are certain resonant frequencies that will cause certain objects to vibrate, and then that can get out of control, and then, well, physical damage can occur to the load, the motor, and that's not good. So what we can do is, if those frequencies are known or discovered, we can skip them as we're accelerating that motor and connected load. Okay, we're on page 20 now. And we're going to go to the bottom here, switching frequency. So this is how fast those IGBTs on the inverter end are switching in order to simulate an AC waveform for us. So the factory default was 4,000 hertz, but they can be changed anywhere from 2,000 to 16,000 hertz. Now, the higher the switching frequency, the smoother the current waveform is going to be. The lower the frequency, the more jagged that current waveform is going to be. So what does that mean? Well, that current kind of helps dictate how torque is developed in the motor, and sometimes we can wind up with something called torque cogging, where the motor really isn't running very well. And so an increase in switching frequency can help with that. So what's a drawback? Well, higher switching frequency, if you can imagine a much larger drive, switching a motor that draws an FLA of 400 amps, well, if we're switching 400 amps 16,000 times a second, that gets very hot very, very fast. So then that motor or drive thermostate is going to increase. So there's give and take with everything. Let's see, let's go on to our next page. Page 21. So this is that DRC menu. So this is our motor nameplate information. So we're in North America. We would make sure that was set to 60. Nominal voltage rating. So that's the motor nominal voltage rating. So it could be 208, 230, 240. Just look at your motor nameplate to determine what that voltage is. Okay, nominal motor frequency as well. Nominal motor current. So all these things are going to be on the motor nameplate. One thing that normally throws people off is this cos phi. What do you think cos phi means that could be found on a motor nameplate? Your answer, of course, would be, well, that's power factor. And it is, but normally we say cos theta. This manual references cos phi, but it means power factor of the motor. If it's known, we would enter that information there. Now, auto tuning, we talked about a little bit in the beginning, and essentially this is a process where the drive sends an electrical signal to the motor, analyzes, the current that gets drawn and how it gets drawn coming back, and then determines the electrical characteristics of that motor itself. So this can be another way to get very accurate control and consistent control of the motor. Now this is a big one, UFT. This represents the torque characteristics of the motor. So we know the factory default here is N, and N stands for sensorless flux vector control for constant torque applications. So this is a constant torque mode. Sensorless flux vector control essentially means we have some very complex algorithms controlling the current going out to that motor that replicate the same type of control that we would have with a DC motor. So very, very accurate speed control. P stands for pumps and fans. This is also called a variable torque or a quadratic torque. And if you look here, we have voltage and we have frequency. Voltage and frequency are not increasing at the same rate. It's variable, and we start off with a lower torque. And then as we increase speed, then we start increasing how that torque is increasing. And if you think about a fan or a pump, then really the only load that they experience would be after they've built up, say, static air pressure in a building or water pressure in irrigation lines. So we don't need a whole lot of power or torque to get the water or air flowing, but as we build up pressure, we need more torque in order to continue to build and maintain whatever set point we've determined. L, simply a constant torque for special motors. Okay, here's switching frequency again. Some parameters will occur in multiple menus. So this is the same parameter, just occurring in a different menu. Maximum output frequency. So this is parameter TFR. This drive can simulate a frequency to the motor maximum of up to 500 hertz. Now, we know how frequency affects a motor. In that, the higher the frequency, the higher the speed the motor goes. It's a formula that you should have learned and reviewed by now. So we can simulate a waveform up to 500 hertz. Now you'd need a pretty special motor in order to do that. And whenever we run a motor above its rated frequency, we say that that is a constant horsepower mode, which we're going to look at in one of the lectures. Factory default is 60. This is different than switching frequency. So this is the simulated waveform, what the frequency of the simulated waveform is. And this right here is the actual switching rate of those electronic components in the inverter in order to simulate this frequency going to the motor. So they're both frequencies, but they are different frequencies. Okay, now we're in our input and output menu. So here we have our type of control. We have 2-wire or 3-wire control. So on the drive, we would go to TCC and push enter, and then we would be able to choose from 2-wire control or 3-wire control or local control. 2-wire control, we're given an example of our wiring. So with 2-wire control, we have forward and reverse. 2 logic inputs that determine if I make logic input 1 true, or if I give it 24 volts, which then we say makes it true, then that motor is going to have a certain output, simulated output, that will cause a forward direction of rotation.